So in part 1, we talked about log, characteristics of logs, properties of logs. In part 2, we're going to be graphing our log functions. So log functions and exponential functions go hand in hand. They're inverses of each other. So inverses, meaning that the x and y's flip. So if something was an x value in my exponential graph, it would now be a y value in my log graph. Or if it's a y value in the exponential graph, it changes to be an x value in the log graph. So if I had a point on my exponential graph for the graph of 2 to the power of x, let's take this point, for example. This would be 2, 4. We'd have a similar point. The x and y would flip on our log graph, so this would be 4, 2 for the log base 2 of x. So the x's become y's, y's become x. They just flip. So on the next page, we have an example. If we have exponential growth, so in our exponential graph, if our base was greater than 1, this would be exponential growth. When we flip it and the x's become y's and y's become x, our graph would look like this. So this is our log graph when b is greater than 1. Now, if we have exponential decay, so meaning our b is in between 0 and 1, our graph would look like this. So it just kind of flips. It goes up to positive infinity instead of down to negative infinity, but it still goes in that right direction. So this would be if our base was less than 1, greater than 0 or less than 1. It flips on the x equals y axis. So that just means your x's become y's, y's become x's. Down at the bottom, we have some characteristics of logs. I'm going to talk about this more on the next page. But important to know here is that instead of our exponential graph, when we had a y-intercept, here we have an x-intercept. And then we're also going to have vertical asymptotes and no horizontal asymptotes. So we will have vertical asymptotes, no horizontal asymptotes. So it's like the opposite of exponential graphs. In exponential graphs, we had y-intercepts and horizontal asymptotes. Here we have x-intercepts and vertical asymptotes. So the domain of our log function kind of flips with what our domain of our exponential function would be. So if we're comparing the two functions, if we had an exponential function and our log function, in our exponential function, our domain was always from negative infinity to positive infinity. Well, in our log function, the x's become y's and the y's become x. So now our range is going to be always from negative infinity to positive infinity. So the domain in our exponential used to be all real numbers. Now our log range is all real numbers. Then our log function, our domain, would be from 0 to infinity, which is what our range would be in exponential functions, from 0 to infinity. Now the 0 could change depending if we have a shift. So an exponential function, that 0 changed if we had a vertical shift. In our log function, that 0 is going to change if we have a horizontal shift. And then a couple other important things to note here. To find the vertical asymptotes, we set the parentheses equal to 0. And to find our x-intercept, we plug in 0 for y. So I'm going to do an example down at the bottom. Let's say we had y equals log base 7 of x plus 4. Let's find our domain, range, vertical asymptote, and x-intercept. Well, let's start with the easy one. What's our range? Negative infinity to positive infinity. Your range for log functions are always going to be all real numbers. Next, our domain and our vertical asymptote are going to go hand in hand. These are going to be the same value. To find our vertical asymptote, we said we set the parentheses equal to 0. So whatever is in our parentheses, we have x plus 4 equals 0. So we just subtract 4 to move it to the other side. So x equals negative 4. So our vertical asymptote would be x equals negative 4. What do you think our domain is going to be?
X cannot equal negative 4.
It would be from negative 4 to infinity. So whatever our value is in our vertical asymptote, that's going to be the number in our domain. How do we find the x-intercept? Plug in 0 into the y. So we have 0 equals log base 7 of x plus 4. I talked about this in part 1. Our brains can't really compute logs, but we can compute exponential equations. So let's turn this into exponential form. So I'm going to start with my base. What's my base? 7. The other two numbers are going to switch positions. So 7 to the power of 0 equals x plus 4. So notice how here it kind of looks like 7. It's attached to the x plus 4. It's not going to be the case. They're not going to be next to each other when you put it into exponential form. Now when we solve this, what's 7 to the power of 0? 1 equals x plus 4. Subtract 4 on both sides. What's our x-intercept? Awesome. X equals negative 3. So as an x-intercept, we'd say negative 3 comma 0. Perfect. All right, so we have transformations of our log functions. These are the same as the transformations from our exponential functions. If you're adding or subtracting on the outside, that is a vertical shift. So if we're adding on the outside, we'd go up. If we're subtracting on the outside, we'd shift it down. If we're adding or subtracting on the inside, that is a horizontal transformation. So we'd go left and right. If we're adding on the inside, we go to the left. If we're subtracting on the inside, we go to the right. If we're multiplying by a negative on the outside, this would be a reflection on the x-axis. If we're multiplying by a negative on the inside, this is a reflection on the y-axis. And when we multiply by a coefficient, so by a constant out front, if it's greater than 1, we have a stretch. If it's in between 0 and 1, it would be a shrink. So let's graph example 7. So it says to graph 3 to the power of x and log base 3 of x. Well, these are inverses of each other. So I'm going to graph the exponential function first, and then I'll just switch my x and y's to graph our log function. So for our exponential function, I'm going to plug in values for x. We're going to plot some points, and we'll get points, I guess, here, x comma y. We're going to plug it in and get some values. So you can plug in whatever you want into the x's. I would recommend plugging in a negative number and a positive number and 0 to get an idea of how your graph looks. So let's plug in -1, 0, and 1. So when I plug in -1, I have 3 to the power of -1. What does a negative exponent do to our number?
Turns into a fraction.
Turns it into a fraction. So this would be 1 over 3 to the power of 1, which would just be 1/3. So our point here would be -1 comma 1/3. So I'm going to go to the graph, go to the left -1 and up 1/3. Next, when we plug in 0, what's 3 to the power of 0? 1. Anything to the power of 0 is 1. So we have 0 comma 1. So we're going to stay at 0, go up 1. And then 3 to the power of 1 would be 3. So 1 comma 3. Awesome. So go the right one and up 3. So that gives us a few points, gives us an idea of the shape of our graph. It's going to look like this. To graph our log graph, so for log base 3 of x, we're just going to switch our x and y's. So the x is going to turn into y, the y is going to turn into x. So my first point is going to be 1/3 comma -1. Just be careful when graphing this. On the test, a lot of people found the correct x and y intercepts, but then put it on the graph in the wrong spot. So be careful when graphing. We're going to go to the right 1/3 and down to -1. Then my next point, again, I'm going to switch the x and the y, will be 1, 0. So we're going to go to the right 1, stay at 0. And then 3, 1 will be my third point. So I'm going to go to the right 3 and up 1. So now our graph's going to look like this. Well, let's find all of our important information here. We'll find the domain, range, vertical asymptote, and x-intercept. Let's start with the easy one. Let's start with our range. We're just doing it for our log graph. What would our range be? -infinity to +infinity. Perfect. Next, let's find our vertical asymptote. What would we do to find the vertical asymptote? We just set what's in the parentheses equal to 0, so we're not looking at the base, just the x. So here, we don't have parentheses to really show us, but it's just x equals 0. So our vertical asymptote would be x equals 0. So my asymptote would go right through 0. So what would our domain be? Zero to infinity. It's whatever number our vertical asymptote was, 0 to infinity. And then lastly, for our x-intercept, how do we find the x-intercept? We plug in 0 into the y. So 0 equals log base 3 of x. We want to put this into exponential form to solve. So we've got 3 to the power of what? 3 to the power of 0 equals x. So what's 3 to the power of 0? So 1 equals x. So our x-intercept would be 1, 0. Which we had as a point here, but just to be super sure, you can always plug in 0. In example 8, we're going to keep that log graph in mind. So the points on my log graph were -1, 1/3, 1, 0, and 3, 1. So this was my log base 3 graph. We're going to apply our transformations to this. So this is our starting function. This is our parent function. We're just going to take our transformations and apply them. So when we apply transformations, you always want to work from the inside out. So starting on the inside, that -1 does what to our graph? -1 on the inside. Not a stretch, but it would just be a shift to the right. So we move it to the right 1. So our 3 points, we're just going to shift them to the right 1. So now our graph is going to look like that. Now we have one more transformation happening. When we have a negative on the outside, what does that do to our graph? It flips it on which axis? Reflection on the x-axis. So this is our x-axis here. This is going to act as a mirror. All of our points above the x-axis are now going below the x-axis. All the points below now flip to above. So we're going to flip our points. So now our graph is going to look like this. So we don't need the other two graphs, the pink and the blue one. These just showed us where we started, applying that shift to the right. And then the orange one is our final graph, applying all of our transformations. So this would be our graph here. Now let's find all of our important information. Let's find the domain, range, vertical asymptote, and x-intercept. Let's start with the easy one. Our range is what? -infinity to +infinity. Our domain and our vertical asymptote go hand in hand, so they're going to be that same value. So how would we find our vertical asymptote? We set what's in the parentheses equal to 0. So x minus 1 equals 0. add 1. So x equals 1. So our vertical asymptote would be x equals 1. We can graph that, just like how we graphed asymptotes before. It's just going to be a dotted line because our graph's going to get really, really close to that, but not touch. So there's our vertical asymptote. What would our domain be?
1 comma infinity.
Awesome. 1 comma infinity. So it's whatever the number is from our vertical asymptote. It repeats in our domain. And our graph is going to the right. It's pointing in the right direction to infinity. When we have a reflection like this, some people think that it points down, so it's going to negative infinity. But remember, our domain is the x values. So looking at our graph going from left to right, our graph is going forever in the right direction, so it's going forever to infinity. Next, how do we find our x-intercept? Awesome, plug 0 into y. So we have 0 equals negative log base 3 of x minus 1. So let's solve. Before I put it into exponential form, I want to get that log all by itself. So how could I get rid of that negative out front?
Distribute it to the parentheses.
Not distribute into the parentheses because it's attached to the log. How would we get rid of the negative out front? Divide both sides by negative 1. Perfect. So 0 divided by negative 1 is still just 0. And then our negative log divided by negative 1 would just cancel. So we're left with log base 3 of x minus 1. Now let's put it into exponential form so we can solve. So we're going to start with our base. What would the exponent be?
0.
3 to the power of 0 equals x minus 1. What's 3 to the power of 0? So 1 equals x minus 1. Add 1. What does x equal? 2. How would I write that as an x-intercept? 2 comma 0. Awesome. Which if we look at our graph, that's exactly where we cross the x-axis. 2 comma 0. All right, let's look at example 9. So here we have a log graph. So we know that its shape is going to look like this. What's the transformation that's happening here?
A shift to the right by 5 units.
It's going to be a shift to the right by 5. So we're going to move to the right 5. Do we have any reflections happening? No. So we know that our shape is going to be like this. Our base is greater than 1, so it keeps that shape. So now let's find all of our important information. That'll help us graph. We've got our domain, range, vertical asymptote, and x-intercept. Start with the easy one. What's our range here?
All real numbers.
All real numbers, negative infinity to positive infinity. How do we find our vertical asymptote? Set the parentheses equal to 0. So x minus 5 equals 0. X equals 5. So our vertical asymptote would be x equals 5. We can draw that on our graph. What would our domain be?
5 comma infinity.
Awesome, from 5 to infinity. We didn't have any other transformations happening. Our graph's going to start at 5 and go to infinity. And how do we find our x-intercept?
Change the f of x to 0.
Awesome, we make f of x 0. So 0 equals log base 4 of x minus 5. Let's put this into exponential form. So I'm starting with 4 to the power of 0 equals x minus 5. What would we do next?
You make 4 to the power of 0 to 1.
Awesome, 4 to the power of 0 is 1.
Both sides.
And then we're going to add 5. Perfect. So what does x equal?
6.
How would I write that as an x-intercept?
6 comma 0.
6 comma 0. So I'm going to go to my graph, go to the right 6, stay at 0, and then we can draw our graph. So it'll look like that. Next, we're going to talk about natural log. So I mentioned this a little bit in, I think, 3.1 and in part 1. If you have log to the power, log base e, this is the same as ln. So log base e of x is the same as ln of x. Log base e is ln. It just looks a little different. It's like the simplified version of it. But to help us when we're graphing logs, if it says ln, you might want to switch it back to log base e. That way we can kind of see it in log form. Might help us a little bit. So just understand that these are the same thing. It also says the domain of ln is all real numbers greater than 0. Same as before, if we were taking the log, you can't take the log of a negative number. If you tried taking ln of -1 in the calculator, you'll end up getting error. It's not going to work. Or if you tried taking ln of 0 in the calculator, again, you'll get error. It doesn't work. Or log of -1. It's not going to work. So you can't take the log of a negative. In example 12, we're going to do everything we were just doing. We're going to find the domain, the x-intercept, vertical asymptote, and sketch the graph. So we'll find the domain, range, vertical asymptote, and x-intercept. Now here it's an ln graph. So if it helps you, change the ln to be log base e. It's the same thing, just changes the way that it looks. So log base e and ln are the same. So this is just a log graph. Let's start with the easy one. What's the easy one? The range. What's our range? -infinity to +infinity. Next, let's find our vertical asymptote. What do we do to find the vertical asymptote? Set the parentheses equal to 0. So we have x minus 3 equals 0, x equals 3. So our vertical asymptote would be x equals 3. I'm going to put a vertical line right through 3. So what would our domain be? 3 to infinity, perfect. We don't have any transformations happening where we flip it around, so it's not going to -infinity, so we're good there. Next, let's find our x-intercept. What would our x-intercept be? How do we find the x-intercept? Set the y equal to 0. So we have 0 equals log base e of x minus 3. So we're going to put this into exponential form. What's my base here? E. So e to the power of 0 equals x minus 3. What's e to the power of 0? 1. Anything to the power of 0 is 1. So 1 equals x minus 3. Add 3. So we get 4 equals x. How would I write that as an x-intercept? 4, 0. I'm going to go to my graph, put a point at 4, 0. Now when I draw my graph, depending if it's growing, if my base is greater than 1 or decaying, it'll look a little bit different. So let's think about it. E, what's the value of E? Anybody remember? 2 point something. Is 2 greater than 1? Yes. So this would just have our growth shape. So it'll look like this. So if we had something, let's say like log of 1/4, log base 1/4 of x, our graph would look like this, where it just switches directions. So it depends on your base. So just keep that in mind. If our base is greater than 1, it's going to keep that shape where it goes down to -infinity together. The base is in between 0 and 1, then it just flips.